Hi everyone, Mr. Coxford here. In this video, we are going to be looking at parallel circuits. So a parallel circuit, the word parallel means alongside. So in contrast with a series circuit, instead of elements being connected one after another, instead they're connected beside each other with their ends connected together, with both ends connected together. Each element is going to be in its own separate branch. Let me draw you a quick little picture of what you might see in a parallel circuit. Might have a little battery here, and then in the first branch, you might have one resistor, and then connected to it in its own separate branch is another resistor, and maybe even in a third branch, you'd have another resistor. These here are the branches of our circuit. For a parallel circuit, there are multiple pathways by which charge can flow in a circuit. Series circuit meant everything had to flow through the same path. Now we can have current flow through this first path, or it could flow through this second path, or it could flow through this third path. There are multiple pathways for the current to flow. Just like we did in series circuits, we have to understand how do we find the equivalent resistance in a parallel circuit. And this is so that we can figure out how much current is flowing out of the battery, and then in turn to figure out what are the voltage drops, what is the current flowing through each of the resistors. So as far as the battery that is pumping charge is concerned, two 4 ohm resistors in parallel would be the same as a 2 ohm resistor connected to the battery. Let's think about that. So here we have a 4 ohm resistor and another 4 ohm resistor connected in parallel to each other. Parallel meaning they're not connected one after another, but they are sort of stacked next to each other, both ends connected together. So we would have current flowing right here, and then the current would split off. Part go this way, part go this way, and then it would connect back together and flow through here. And this, we're claiming, is the same as a single 2 ohm resistor. And why is that? Why does the equivalent resistance of two 4 ohm resistors come down to 2 ohms? Well, let's think about it. If you are a particle, or there's a bunch of particles flowing within this circuit, and there are multiple pathways for you to travel through, will that increase the resistance, increase the flow, will it increase the resistance or decrease the resistance to that flow of charges? Well, if there's more paths, there's going to be less resistance. So having circuit elements in parallel will decrease the total resistance. Another example, if we have, let's say, 3 6 ohm resistors, so here's a 6 ohm resistor. Let me draw that 6 a little better. Try that one more time. 6 ohm resistor, here's a 6 ohm resistor, and here's a 6 ohm resistor. That is the same as, any guesses? That's also the same as a 2 ohm resistance. So by having 3 identical resistors in parallel, the resistance becomes a third of what it was before. So in general, this is what we can say about equivalent resistance. It's a complicated expression, and it will just take some practice to be able to use it and understand exactly what's going on with it. But here's what we'd say is that 1 over the equivalent resistance, and this is for parallel circuit elements, so 1 over the equivalent resistance for parallel circuit elements is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, plus keep going. Now there's a simpler way to write that, and that would look like this. I like to use it this way because it gives you directly what the equivalent resistance is. It says that the resistors in parallel, the equivalent resistance is, and I open up a big bracket, 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance plus etc. Close that, add those all up together, and then inverse it. To the power of -1 is simply the reciprocal. It's 1 over that. You have that button in your calculator that you could use. There's a little -1 next to the -1 button. You can look at your calculator right now, see if you can find that button. That's the handy button. Once you do that 1 over plus 1 over plus 1 over equals, then hit the to the -1 button, and it will inverse that. So what the effect of that is when we add them all together, it will end up with a lower resistance than any individual resistor within that circuit. Because as we open up a new branch, no matter how big or small that resistor is, if you open up a new branch, more charges will be able to flow through that branch of the circuit, reducing the overall resistance to flow within that circuit. Now, within a parallel circuit, voltage within a parallel circuit, the voltage drop across each resistor in parallel is equal to the voltage supplied by the battery. The voltage supplied by the battery, the voltage drop across each resistor is equal to the voltage supplied by the battery. So if the battery supplies 9 volts, you look at the voltage drop across the first resistor, it's 9 volts. You look at the voltage drop across the next resistor, it's 9 volts. Every resistor in parallel is going to have a 9 volt drop across it. And then using that idea and Ohm's law, we can then figure out, using the voltage of the battery and the equivalent resistance of our circuit, that can give us the current flowing out of the battery. And now for a parallel circuit, it's a little bit different than a series circuit. In a series circuit, the current was the same everywhere. In a parallel circuit, it's not the same everywhere. In fact, the current supplied by the battery is equal to the sum of the currents through each resistor or through each branch. Here's what it says. The current through the battery is equal to the current through the first branch or the first resistor in parallel plus the current through the second branch, or the second resistor in parallel plus the current through the third branch, etc., etc. Let's draw a little diagram and see what that looks like. Here's 1, 2, 3 circuit elements. And what we're going to have is this current that is flowing out of the battery. And it's going to get that current, all of that flow, is going to hit this first little junction here. And it's going to split off. Part of it's going to flow down this first branch, and part of it's going to continue on this way. And the part that flows through this branch is I1, the current flowing through the first circuit element. The rest is going to continue on. Then it's going to hit this next little junction here, and part of it's going to flow down this way, I2, and the rest is going to flow this way through this third branch, I3. And then this I3 is going to flow back here, and it's going to combine with I2, and then that's going to flow here, and then that I2 and I3 combined is going to connect back up with I1, and that's going to connect back up, and we're going to get back that original current. So all the flow is going to split off into its individual branches, and then it's going to flow back together. Let's see that in practice. So here is a slightly more simple circuit, and this is actually the circuit in our next example. But we have a battery and we have 2 resistors, and I'm going to show the current here. And what we can see is this is a pretty big battery, a 60 volt battery. We have a 15 ohm resistor and a 30 ohm resistor. And what you'll notice is here is the flow. It's pretty fast. over here coming out of the battery, and then you see it splits off. And as it hits this junction here, some of it goes down and some of it goes forwards. Notice that the flow downwards is fast because it's a smaller resistor, but not quite as fast as the current flowing out of the battery. And the current that's flowing through the bigger resistor, it's a little slower, much slower than the current through this 15 ohm resistor. But then when they join back up, they will combine to equal the current that was flowing out of the battery. And also notice this. I'm going to open up this switch. Notice what changes and what doesn't. Notice that the current flowing out of the battery decreases. It slows down. But notice that the current flowing through this branch here remains the same. And that's because we're always powering this circuit element here, whether or not this next one is connected. All right, let's see. Let's go to this example. So we're going to look at this circuit, and we are going to, just like in the previous video, we're going to find the total equivalent resistance, the current flowing out of the battery, voltage drops, currents flowing through the different resistors. So let's start by finding the total equivalent resistance of the circuit. Req, which in this case is for circuit elements for resistors in parallel, which is this little equation here, 1 over R1 plus 1 over R2 to the negative 1. So it's 1 over 15 plus 1 over 30 to the negative 1. 1 over 15 plus 1 over 30, if you figure that out, ends up being 3 over 30. Flipping that, 30 over 3 will give us 10 ohms. So the equivalent resistance of a 15 ohm and a 30 ohm resistor is 10 ohms, less than either of those two resistors. Now let's figure out the current flowing out of the battery. Current flowing out of the battery, I bat, is the voltage of the battery divided by the equivalent resistance. So if we have a 60 volt battery and that 60 volt battery is experiencing 10 ohms of resistance, that equivalent resistance, then 6 amps is going to be flowing out of this battery. 6 amps is going to be flowing right here. Now, we want to figure out how is that 6 amps going to be splitting down each of these two branches. To do that, we're going to use Ohm's law again, which means we need to know the voltage and the resistance to be able to calculate the current through each branch. And so the voltage drop across the 15 ohm resistor, well, from what we learned earlier, the voltage supplied by the battery is going to be equal to the voltage drop across resistors in parallel. So V bat is going to equal to V1 is going to equal to V2, which is 60 volts. There's going to be 60 volts dropped across each of those resistors. So then to figure out the current through this first circuit element, rearranging Ohm's law, V is equal to IR, which gives us I is equal to V over R. So V1 over R1, 60 volts dropped over this 15 ohm resistor means that 4 amps is going to go through this first branch here. Now, if we have 6 ohms or 6 amps flowing into this junction here and 4 amps are flowing down, I think we can safely say that that means that 2 amps must be flowing through this branch of the circuit. Well, let's confirm it using Ohm's law. I2 is going to be V2 over R2. Again, that circuit element, that 30 ohm resistor, is in parallel with the 15 ohm resistor and the battery. And so there's a 60 volt drop across it, and it's 30 ohms. And so in fact, it is 2 amps flowing through there. And then what you would see is that once this 4 amps flows back down and the 2 amps flows, they will recombine back to 6 amps in this part of the circuit where the battery is. So what is the total current flowing through both resistors? I1 plus I2 is 4 amps plus 6 amp, or plus 2 amps, and this is 6 amps, the current that is supplied by the battery. Let's just quickly confirm that in our diagram or our simulation here. Let's look at first the voltage. We can see the voltage supplied by the battery, 60 volts, and everywhere along this top branch, everywhere that's connected to it simply by wires, notice it's all 60 volts everywhere here. Compared to the bottom of the battery, we have 60 volts of potential at the top here. And then as we go through this first circuit element, we go down to 0. And as we go down through this second circuit element, second resistance, we're back to 0 volts as well. The other way to see it is comparing the potential from the top of the battery, where if we're comparing anywhere on this wire, it's all 0 volts. There's no difference in the potential compared to the top of the battery. But as we go through this first guy, we drop 60 volts. And as we go through the second guy, we drop 60 volts. Okay, and then let's look at the current really quick to confirm it. We can see 6 amps flowing through this first part, 4 amps flows down, 2 amps flows to the right, the 4 amps flowing down here, and the 2 amps flowing down here combine to give us 6 amps. Okay, I hope that was helpful, and I will see you in the next video.